Yeah, I can clearly see everyone's in exams. Only 16 people in class today. Nice. All right. So we're in week 5, class 1. All right. And also, homework 3 is due today. Make sure you get that in so that I can post the solutions at midnight tonight so that you can use them for your exam on Thursday. And also, homework 4 has been posted, and that's due next Tuesday. All right. Okay. So we are looking at the kinetics of particles, right? We're continuing on with this topic. But today, what we're looking at are energy. Well, today and our next class, we're going to be looking at energy and momentum methods. And today we'll focus on setting up the energy stuff. All right. So in general, you know, when you're looking at your problems, right? When you're looking at force and acceleration, what you're concerned with is Newton's second law, right? When you're looking at velocity and position, right? We know that we can solve this using kinematics, but an easier way to do it, as we're going to start setting up today rather, it's going to be looking at work and energy. All right. And then when you're looking at velocity and time, again, we've looked at this from a kinematics point of view, but we'll see in the next class that we're looking at impulse and momentum when velocity and time are coming into the picture. All right. So let's start with work and energy, right? So the first thing that we need to define is what is the work of a force. All right. So let's say that you've got some force F like that, right? And what ends up happening is that it's acting on your particle P, right? And what ends up happening is that you end up changing position from here to, let's say that you go somewhere to here to P prime, right? And you've defined the position relative to some point, as we know that we have to do, right? So you have some R like that, and then you've changed the position ever so slightly that this new position, let's say, is R plus dr like that, right? In vector form, obviously, right? So that this displacement here is dr, right? Let's say that the angle between the force and this displacement is alpha. So how you define the work of a force is basically using this expression, capital U, right? So the small change in work, du, is what we are calling the work of the force F, right? And the way that that's defined is just your vector F dotted with the change in position dr, right? And let's say that this expression is number 1. This here, take note, this guy here is the dot product. All right. And if you know that dr has a scalar value, let's say it has a scalar value ds. So let's say that this has a scalar value ds, right? So you can write this expression, and your force F obviously has a scalar value F. You can write this expression as F times ds times cosine alpha. And that just comes from the definition of your dot product, right? You can also write this up, as we know, from the dot product in the components in the ijk expressions, right? So this can be fx times dx plus fy times dy plus fz times dz, like that. right? So we take a look at ultimately, what is this work? Is it going to be a vector or a scalar?
Scalar.
It's a scalar, right? Because all dot product of two vectors is going to be a scalar quantity. So work is a scalar quantity, right? And its dimensions are the dimensions of length times force, right? Which, if you work in SI units, is this quantity called joules, right? So you have J. Right? Next, you can define the work for a finite displacement. So you have the work of a force with finite displacement. Right, so this is changing from, let's say it changes from position 1 to position 2, right? And you are integrating you're summing up all of those small amounts of work that the force does. And that is usually written as U, subscript of whichever position you're going from and whichever position you're going to. So position from 1 to 2, right? And if, whoops, let me just write that again in the next page here. So you have 1 to 2 du, that's basically u of 1 to 2, like that, right? And let's say that you have some force, let's say that it's T, and this force is in the direction of the displacement. Right, so if you plot it out, so you have ft like that, and you have your position on the x-axis like that, and let's say that you're going from position 1, from some position 1 to some other position 2, right? And your force changes something like that, right? So the area under this curve is going to be this total work over here. So it's the work done from moving from this position to that position. So this is equal to your u of 1 to 2, like that, right? So you can find this out exactly if you do an integration over two different positions, A1 to A2, let's say f dot dr, like that. Or as we saw over here, you can just, if it's a tangential force, right, or you find the tangential component, you have ft times ds, like that, and you only have it being a complete scalar quantity, right? This is tangential, like that. All right, and in general, now you start getting into some more abstract concepts like signs and directions and things like that. So in general, when the displacement is in the direction of force, right, the work done from moving from one position to the other is positive, right? So positive, like that, right? And in general, when the displacement is in the opposite direction, right, the work done is negative, right? So is negative like that, right? Also, what makes things easy is, make sure that you define a coordinate system and you figure out your positives and negatives in relation to that coordinate system. All right, next, you want to look at, let's say, we're starting to look at examples now. So let's say that we're looking at, some particle which is in the form of a box, right? It moves down, it moves up a path rather. So it starts off in position 1 and you're at position 2, right? And with the coordinate system that you've defined, not only are you defining directions, you also have to define what's known as a datum, right? A reference line, right? So initially, the position is y1, and then finally, the position is y2, like that, right? And if you're seeing it in any general position, right? The only force that's acting on this body, right, is the weight, which acts downwards, right? The next, when you're looking at the work of the force of gravity, right? So that's going to be from position 1 to position 2, so u of 1 to 2, right? Is the work done going to be positive or negative? The work by the force of gravity?
Be negative.
It'll be negative, right? Because your displacement is in the opposite direction to which your force is acting in. All right? So this is going to be minus, and you're integrating from your position 1 to position 2, w times dy. And here, the note is that it is negative because force is in the opposite direction to the displacement, right? And the overall chain with a simple integral, your weight remains constant, right? So the work done is just going to be w minus w times y2 minus y1. Right? Another way, as we said, you can look at the weight and the displacement relative to each other, or you can look at it relative to your coordinate frame as well, right? So you can also look at it in the sense that the weight in the negative y direction and the displacement is in the positive y, right? So overall, the sense for your energy is going to be negative. All right. Next, you have work done due to gravitational force. Right. So let's see. We can probably fit it in here. All right. So let's see. Say that you're going. You have some body that's traveling on a path. You've got the main body, which is big M. Got the small body, which is rotating around the big body M, like that, right? You've got, say, initial position, R1, got, whoops, and another position, R2, right? And on the body itself, right, when we're looking at defining our coordinate frame, right, you'll have your coordinate system such that you're looking at the radial and transverse components, right? That the radial component always points away, but here the force is going to point in the opposite direction like that, right? So you have F in this direction and you've got, let's say, minus F in that direction, right? So here, when you're looking at your small change in energy, right, that's going to be minus F because it's in the minus F direction in reference to your coordinate system that you've defined, dotted with dr, right? Dr we're assuming is in the positive r direction, right? So in general, when you're starting things off, you assume that to be positive, right? And if you look at it in terms of the scalar quantities, that just ends up being minus F times dr like that, right? Because that's how the directions are. They're in the same direction, and the dot product will just end up being the product of the two, right? And we know what the magnitude of this force is, right? From Newton's law of gravitation. So that's just minus gmm over r squared times dr, right? So when you're doing your finding out how much work is done from moving from position 1 to position 2, right? You have the negative sign, comes out outside. You're going from position 1 to position 2 like that. You're integrating gmm over r squared dr. And what you end up with is the minus sign goes away. You get gmm 1 over r squared. The integral becomes minus 1 over r, right? So it's just 1 over r2 minus 1 over r1 like that. All right, how are you guys doing? Questions?
For this example, you're saying the work done from little m moving from R1, R2, right?
That's right, yes.
Okay.
So this is position 1 to position 2, right over there. Thanks for asking that. Yeah, R1 to R2, right there. Right, so if we're moving from position 1 to position 2, it's 1 over R2 minus 1 over R1. So the sense changes. That's what happens when you're. I've gotten into some very big arguments about signs of things and things like that with physicists. Like, how can potential energy be negative? No, this is the work. This is not the potential energy. So this is the work done by the gravity force. And this is absolutely 100% correct. I'll fight someone if they want to fight me on that. So. All right, ready to move on? So there's a couple of things which make our lives easy when we're looking at work and energy, right? So basically, there are forces that do no work. Right, and this is the case where your change in displacement is going to be 0, or potentially, you know, the angle is going to be 90 degrees, right? So when you have reaction at a frictionless pin, and let's say that it's supporting a rotating body or something like that, that reaction is going to do no work ever. All right, again, if you have the reaction of frictionless surface, right, when body moves along that surface. Why? Because the movement is perpendicular to the direction in which your reaction force is going to be, therefore it does no work. Right, then you have reaction of let's say, and these are just some examples. There's obviously more examples, right? But in general, these are some things that you might more commonly see than others. So you have a reaction, a roller moving along its track, right? And also in general, when you have a force that is always normal to the path, right? And all those reactions are basically aligning to this main idea over here. All right, okay. So now let's take a look at these things a bit more carefully, right? So let's say that you're moving along some curved path, right? And that you're moving from, let's say, position 1 to position 2, whoops, to like that, right? And what you do is that at any position on your body, let's say that you have a force which is acting on it, right? We know from our good work in kinematics that we can take the components of this, right? So you can take a component of this in tangential direction, and you can have a component that is going to be in the normal direction, right? So now let's take a look at this tangential force a bit more carefully. So if you look at this tangential force, right, what is that going to equal from Newton's second law? That's just the mass times the acceleration in the tangential direction, right? And we know that this acceleration in the tangential direction is equal to what in terms of the velocity?
Oh, like the derivative.
Derivative.
That's right. So it's just going to be dv over dt, right? And then what's the acceleration in the normal direction?
V squared over R. Or
V squared over rho, right? So that's your radius of curvature. Absolutely right. Okay, so this is equal to that. So now we can also, we know from our mathematical juggling that we can write this as dv over ds times ds over dt, like that, right? Where s is the change in position, right? And here, ds over dt is nothing but what? It's the velocity itself, right? So you end up with the expression mv times dv over ds, like that, right? So this is equal to v, right? So therefore, the expression, if you send this ds over to the other side, you get that ft times ds is equal to mv times dv, like that, right? Can you guys see where we're going? When you're moving from position 1 to position 2, right, you're going to integrate for those two positions at 1 and 2. So let's say S1 to S2, ft ds, right? So this is the work done from position 1 to position 2. Mass remains constant, right? So the mass comes outside, and you're changing the velocity from position 1 to position 2, v dv, right? And when you take the integral of this and you plug in your two velocities, what do you end up with? You end up with 1/2 mv2 squared minus 1/2 mv1 squared, right? And here you end up with the expression, which is going to be the lead up to energy conservation, which we'll take a look at next week, but we're not calling it energy conservation today and for the homework that you guys have today, right? So That is your work done by the force from position 1 to position 2, right? This is your kinetic energy at position 2, and this is your kinetic energy at position 1, right? So here you have T, which is equal to 1/2 mv squared. That is the kinetic energy. All right, so the expression that you end up with is that the work done by the force F is equal to the change in kinetic energy. And we're going to be using this expression, right? And you might see different variations of it. You might see that the work done plus the kinetic energy at the first position is going to equal the kinetic energy at the second position, right? So you might see the equation be used in that format as well, right? And then you have the work. So basically, we're just writing out what this expression says, right? The work, force F is equal to change in the kinetic energy. So kinetic energy writing as Ke going forward. All right, questions, guys? I'll be right back. Got to run to the bathroom real quick. Man, these morning classes always. All right, I'll be right back. Mask. All right, guys, let's get back into it. All right, so if we take a look at a quick example, right? So let's see, we have, let's say we have something like a pendulum, right? So a pendulum fixed on top, right? It starts from rest, some position, let's say V equals 0, goes on, and let's take a look at it when it is completely straight, right? So this position, so you have position 1, position 2, you're saying what is this velocity going to equal, right? So let's say the length of it is L, and it obviously moves in a circular path, right? So if we take a look at particle, right, you'll have the tensile force along the the string, whatever's joining this to that. So you have that force. So let's say that there's that force P, right? It acts straight up like that, and you'll always have the weight which acts downwards, right? So question is, from this position 1 to position 2, does this force P do any work? So does this force P do any work?
No,
Why not?
it's normal to the path.
It's normal to the path, right? This force P is always going to be normal to your path. So the force P does no work. Oops. Because it is normal to the path, right? So what we can say is, from this expression here, and again, we're not calling it conservation of energy because we're not taking a look at potential energy. We're taking a look at work done right now. So we can use this expression over here to find out what the velocity is going to be, right? Because we know that the initial kinetic energy plus the work done by the force to move from position 1 to position 2 is going to equal the final kinetic energy, right? So the initial kinetic energy we know is 0 because it starts from rest, right? The distance moved in the direction of the weight W is how much?
L.
L, right? It's just, so this work done by the force W is just going to be WL like that, right? Because, and also it's positive. Why is it positive? Okay, different question. Would it be positive? Would it be negative? I gave you the answer that it's positive. Why is it positive?
Maybe
'cause-
the displacement going.
Yeah, the displacement is what?
Yeah.
So it's positive because the displacement is in the same direction as which the weight is in, right? So relative to each other, they're in the same direction. So because displacement in direction of the weight. All right, and that is just going to equal your final thing, right? So just half times the mass. We're given W, so the mass is just equal to W over G times V2 squared, like that, right? and you do your mathematical juggling, you get that V2 is equal to the square root of 2 GL, right? Very famous expression for pendulums released from rest, from a horizontal position. All right. What was beautiful here? You found the velocity without doing Newton's second law, without finding out what the acceleration was, without doing what the integrating is. So now, for those of you guys who had fun solving problem 1 in your homework 3, this is an easier way to do it.
I had a question. I already used conservation of energy. Do you mind?
That's okay. That's okay. Yeah. If you guys want to go ahead and jump the course, that's fine. That's okay. But don't use conservation of energy in your exam on Thursday.
Okay.
Thanks. Right? That was the super beautiful, easy thing to do here, right? So in general, you can't use this work done and kinetic energy principle to find the acceleration. You'll always have to look at Newton's second law for that. All right, and last we look at power and efficiency. You guys have a bonus question with this in today's homework. Right, the definition of power is the rate of doing work. Right, you're attaching a sense of time to your work done, right? And it's defined as du over dt, right? And we know that du can be written as f dotted with dv, dividing this whole thing by d, oh, sorry, not dv, dr. Right, so basically power, just f dotted with dr over dt, which is just the velocity. All right. Units of power are, what is the unit of power? Get it? What? I just said it. What is the unit of power? Really bad joke. All right. So that's an SI unit, and that's equal to joule per second. All right. And the important thing that you define when you're looking at power is this quantity, which is defined by this expression eta, which is the efficiency, right? And that is equal to your output work divided by the input work. Good. All right.
What symbol is that?
Eta. Eta. Hey man, take it up with the Greek people, not with me. So yeah. All right. Stop recording.